All right. All right, so today we're going to go way back in the book again, all the way back to chapter 5, which we skipped a long time ago, and we're going to catch up on it now. The reason we skipped it before, the reason I like doing it later, and my colleagues also, is it really doesn't fit in with anything else. Nothing we've learned so far, well, not nothing, but most of the stuff we've been working on for the last several weeks had nothing to do with nuclear chemistry, and so to just kind of like stick it in the middle would have been, I think, confusing. So now that we've talked about most of the other regular chemistry stuff, we can go back and hit some of these things that are a little bit different, like nuclear chemistry and then the organic chemistry coming up next week. The reason nuclear chemistry is so different is because it takes place in a totally different part of the atom. So what do you think is the difference? Well, what do you think that word nuclear chemistry means? What's happening? Where are the reactions happening? Yeah, in the nucleus, right? So where have they been happening in all the other chemistry we've been studying? Yeah, the electrons. It's all been about losing electrons, gaining electrons, sharing electrons, all that kind of stuff. So now we ignore the electrons and we look at the nucleus, just the inside of the nucleus. So let's review a little bit from way back when we looked at individual isotopes and some of the ways that we wrote that. Let's remind ourselves how to do that. So if I wrote something like this, what does that mean? We did this before, but it's certainly been a while. What are those numbers? What do those numbers tell us? Nope. What about protons? Yeah, so it's probably good we reviewed this. So which one tells us the protons? The bottom, yeah. The 6 is the atomic number, and that tells us the protons. Up on the periodic table, that's the blue number that we said the atomic number. So then what's that 14? Right, that's what we call the mass number, which is the neutrons plus the protons. So we've got number of protons here, the atomic number. And then we've got protons plus neutrons here. Now we haven't really messed with this kind of stuff for a while because when we do like molar masses and all of that, we use averages of mass numbers that we get from those red numbers on the periodic table. But if you remember way back to when we were first learning about the individual bits of the atom, we said that, well, actually, you've got to have a count of neutrons and protons, and we call that the mass number because you can have these different isotopes that have different mass numbers. So like for carbon, you can have carbon 14, carbon 13, carbon 12. Those are all known as different isotopes. So those would only differ by the number of neutrons, because if we change the number of protons, we have a different atom, right? So those will have a different number of neutrons. And now we're going to use that talking about nuclear chemistry, because that can actually change in the course of a reaction. Not the chemical reactions like what we've been doing, but special reactions called nuclear reactions can change these numbers. All right, so we're going to do this. The book does it kind of like in 2 sections. We're going to put it all together. But there's a couple of terms that we need first. First, radiation. Now, radiation is a very general term. It is not specific to nuclear chemistry. Radiation is any emission of energy. So when you turn on a light, radiation comes off of the light. The radiation that comes off is visible light. When you make a call on your cell phone, you transmit microwaves in that case to the cell phone tower, and that's radiating energy. So that's radiation also. Radiation does not need to be dangerous. It's not necessarily bad for you. It has kind of a scary connotation, but it just means any energy coming off of something, coming away from something. You know, it could be light, you know, an LED, whatever. So then, this is where we get a little bit different, where we talk about radioactivity or a radioactive isotope. So radioactive isotopes Just see if I like the book's definition. A radioactive nucleus or radioactivity is we'll say radioactivity is production of radiation via nuclear decay. What that means, and we'll see some examples pretty soon, is that the nucleus actually breaks down, breaks apart, and in the process of that breaking apart, emits different kinds of energy, different types of radiation. And so then a radioisotope is an isotope or a particle that spontaneously emits that radiation. So you can make, like when we did our flame tests, we made those ions emit radiation by heating them up in a flame. Because when we saw that light coming off them, the red light, the green light, whatever it was, that's a type of radiation. The difference with this stuff is a radioisotope or a radioactive isotope will emit that radiation all on its own spontaneously, and generally because of a way that the nucleus is kind of breaking down, changing energy, falling apart, that kind of thing. So it's a nuclear process. The radiation that we saw, like in the flame tests, was coming from the electrons, not the nucleus. So that's kind of the difference here. So let's look at some of the ways that these particles break down and the type of radiation that we get out of them, which is a little bit different from regular old radiation that we've seen so far, like visible light or whatever. All right, so the first type of decay that we're going to look at is called alpha decay. So we'll say types of decay, and one alpha decay. And these particles are named as such because when they were discovered, nobody knew what they were for a long time. They knew they were different and they behaved differently, but they didn't know what they were. So that's why we have these weird terms like X-rays. Nobody knew what an X-ray was, so it's just, I don't know, some kind of ray, and it's an X-ray. Cathode rays is another one. A cathode ray is an electron that's being, like an electron beam. But they didn't know that at the time, so they gave it a different name. So same thing here. We know what these particles are now, and I'll tell you in a second, but originally they didn't, so they got the name alpha particles, and it stuck. So alpha decay is when, let's say, a nucleus emits alpha particles. Now, what are alpha particles? Alpha particles are helium nuclei. So an alpha particle has, a little bigger so I can write in it, has 2 protons and 2 neutrons, which means it's charged because each proton has a positive charge. And it doesn't have any electrons. So when we say it's a helium nucleus, remember before we defined any particle that has a certain number of protons is named that element. So if there's a particle that has 2 protons in it, we call that a helium, even though it's different from the helium neutral atom. So it's a helium nucleus, it's got 2 protons and 2 neutrons. And that means that there's a couple ways to write it. We can write it as a helium nucleus like this. So we can say it's helium and it's got 2 protons and a 4 overall mass. Or sometimes we just stick with that letter alpha and we just call it an alpha particle like that. So what is this decay process that we're talking about? Decay is when a nucleus emits an alpha particle. And because it's a type of chemistry, it's nuclear chemistry, we can write an equation that shows that happening. And these equations are actually, they're very different from what we did before, but they're, I think, easier to write. So this is what a nuclear equation looks like. Let's take uranium-238. So we got uranium, which has an atomic number of 92, and we're specifically looking at one isotope, 238. So the first thing to remember is that when we have decay, that's kind of like a decomposition reaction, which means it's not things coming together, it's things falling apart. So we're just going to start with this one thing, and then it's going to fall apart. So here's how it falls apart. We draw the arrow, and if it's alpha decay, it means we lose an alpha particle. So an alpha particle is a particle with 2 protons and 4 total mass. And then we balance the equation just like we did before. But this time, instead of balancing by putting numbers out in front and doing all that stuff, we're just balancing the particles. So if that nucleus lost 2 protons and 4 overall mass, so 2 protons and 2 neutrons, that means that whatever's left over has to have all the rest of it. So the particle that's left over is going to have 90 protons instead of 92, because 2 of them came out in the alpha particle. And instead of a 238 mass, it's going to have a 234 mass, because 4 of those particles came out with the alpha particle. So if you notice, the numbers on the left, if you add them all together, there's just one of them, are the same as the numbers on the right. The top numbers and the bottom numbers add up. You see that? So that's all you have to do for nuclear reactions, is just make sure the numbers add up. Now the last step is to fill in the symbol with the new element. So what's the new element that goes there? It is 90, which would be TH, thorium. So we look up the atomic number on the periodic table, which is now 90, and we just write down the symbol for element number 90. And that's the whole equation for alpha decay. All right, here, so you try one. Write the equation for the alpha decay of americium-241. Okay, what are the products? Still alpha decay. So you do it the same way. Put your particle first, and then just subtract from the initial numbers and figure out what the other numbers should be. So 95 minus 2 is 93. 241 minus 4 is 237. And we look up the periodic table, find number 93, and that's NP, Neptunium. All right, see how that works?
So alpha decay is always going to
Yeah. That helium is not, remember, it's not really helium. It's an alpha particle. But an alpha particle has 2 protons, so it's technically helium. Because anything with 2 protons has to be called helium. So that's where this comes from. That is the alpha particle. So if you were writing an equation for alpha decay, you always start with that, and then you put whatever is left over.
So then always use helium
In alpha decay, yep, because that's the alpha particle. If you didn't like that, you can use this instead, this alpha symbol. But I believe the book exclusively uses the helium type symbol. So, all right, so that's the alpha particles. So what are alpha particles? Well, they are these little things, and they come off of these radioactive elements. And let's talk a little bit about what they do, like what are their properties. So alpha particles are large. I mean, relatively speaking. Obviously, they're tiny because they're just a nucleus. But compared to other types of radiation, they have a lot of mass. Remember, most radiation is just energy. It has no mass at all. So alpha particles are, by comparison, pretty large, which means when they hit things, they can do some damage. They're also charged. Remember, they have a positive charge because they don't have electrons. So they can rip electrons off of other things. They can bombard other atoms. They can cause some damage. Now, it's true that they can be very damaging, but they can't travel very long distances because they're so big that they tend to bump into air molecules. So if you had a rock that was highly radioactive, emitting alpha particles, that was sitting on the table or something, it's of no danger to us. Even though that radiation is ionizing radiation, it's radiation that is shooting these particles off that could really do some damage, it's so far away from us, by far away I mean like at least a centimeter, that the air just takes care of those alpha particles and they present no danger to us. Even if we put it right on our skin, the very first layer of anything will absorb those, and we'll do some tests in lab that show that. Alpha particles are really easy to block, so they don't really make it through anything. Where do you think alpha particles can become a problem then? If they're pretty easy to block and they're not really like an external threat, if there's alpha radioactivity around, when does it become a problem? What?
internal.
When it's internal, right. So if you get radioactive materials that emit alpha particles inside your body, now there's nothing really protecting them from damaging organs, damaging cells, things like that. So a lot of the most damaging radiation, things like radioactive iodine, which is both a therapy and something that can be dangerous to you, are alpha emitters. Actually, I should look that up. That may not be true. Is iodine an alpha? Well, okay, yeah. I don't know. We'll find it. So some alpha emitters can be a real problem if they get inside your body, because they can cause problems. I don't see that one. Radium, that's what I'm thinking of. So radium-226 is a radioactive element. So let's look at a equation again using radium-226, but I'm going to write it a little bit differently. So sometimes an isotope is written like that instead of in the symbolic form. So now, see if you can write, just from that information, can you put together the whole equation for radium-226 undergoing alpha decay? All right, so were you able to get all the information you needed for that equation together? What does that 226 number tell you? Right, the mass number, right? The neutrons and the protons. So we can go. And then if we want that bottom number, we can just look it up. Because we look up radium on the periodic table, we get 88. And then we're going to write our alpha particle. All right, and there you go. No, Rn is radon. Rn is radon. Yeah. Radon is a gas that accumulates in your basement and causes problems. You got to test for it. Again, because that's also radioactive. But in this particular case, we're talking about radium, which is Ra number 88.
So basically, with all these, you're taking the atomic number and the mass and just minusing 4 and 2, and that's it.
That's it. Yeah, not too bad, right?
I like these better.
You like this better? Okay, good. Yeah, good. So this one, radium was discovered by Marie Curie famously, and ended up causing a lot of problems for a lot of people. It probably killed her. Yeah.
Wait, so that is 86 protons.
88. Oh, you mean the product?
Yeah.
Yeah, you're right. I'm sorry. Yes,
Yeah, that's what I was
that's what you were talking about. I'm sorry, of course, yeah. So you start with radium and then radon. Thank you for correcting me. So yeah, radium caused a lot of problems, probably because, of course, when radioactivity was discovered, everybody thought it was really cool because it made things kind of glow sometimes. So you had these kind of rocks that emitted these particles, and it's not the radioactive elements themselves that glow. So like if you had a bunch of radium, it doesn't glow. But the energy produced by the alpha particles being emitted hits other elements and causes them to glow. So it's transferring the energy to other things that makes them glow and kind of gets that thing that we always think about with radioactivity, where you've got your like glowing rock. That's actually has nothing. It's not the radioactive element itself. It's hitting a phosphor or a screen or something. So of course people thought this was really cool and didn't really think that it might be dangerous. So for a long time, people would play with it. There was a huge market for health benefits of radium. So people would sell radium creams and radium pills and all this stuff that was, because it was assumed that like this magical substance would make you healthy. But of course, it just gives you cancer and you die. So not a great idea. But there's all kinds of old ads. You can look around for like radium creams and other bad ideas. For a long time, until well after it should have stopped, clocks were, radium was used to paint clock faces, to paint watches and clocks, like the hands and the numbers, so that they would glow in the dark. And the thing that's that, if you have a clock that has radium in it, it's not dangerous to you. Like we said, it doesn't, the radioactivity doesn't go very far. The problem is with the people who made that, because what they would do is lick the brushes to get a really nice thin tip, and then use that to paint the radium. And they were getting sick, and the companies were knew that it was really dangerous and did not tell the mostly poor women workers who were doing the actual work. And it was the, I think it was the first large class action lawsuit in the US that was won when they were able to prove that the company knew of all these health risks to painting with radium and didn't do anything about it. All right, so that's alpha particles. Let's look at the next category, which is beta decay. So these things were discovered and just kind of given these generic names because nobody knew what they were. So you had alpha particles and then you had beta particles. They knew that alpha particles and beta particles behaved differently, but didn't really know what they were until sometime later. And we found beta particles are actually electrons. So a beta particle is sometimes written as this, sometimes written with an E to show that it's an electron. The book uses the E exclusively. This numbering is a little bit stranger because there is no -1 element. But it's the idea that this electron has a -1 charge. So we call it, we put -1 down there. Now, electrons do have mass, but their mass is effectively 0 if you remember from way back because they have such a small mass compared to protons and neutrons. So the amount of mass in an electron is super, super tiny, so we can think of that as effectively 0. So that's beta particles. Let's look at an example of beta decay, and you'll see the equation comes out a little bit differently. One isotope that undergoes beta decay is carbon-14. So we start the same way. You start with your isotope, and then you're going to first write the particle. In this case, it's this electron. So we've got -1 and 0. What do we put for the other numbers here to make it all add up properly? Top number's kind of easy. What would you put there? 14, yeah, because we're not changing mass. What happens in the bottom? Yeah, it's got to be 7, right? Because the sides have to work out, and 7 plus -1 is 6. So that ends up being nitrogen. But if you think about that, it doesn't really make a whole lot of sense. How do you lose an electron and then magically gain a proton? And I don't know if you thought about this at all, but it's weird anyway that an electron would be emitted from a nucleus. Because remember, this is nuclear chemistry. So we're not saying one of the electrons around the nucleus shoots off. We're saying an electron actually comes out of the nucleus at very high speed. Kind of. What's happening is a neutron, in the course of this reaction, the way that these particles are formed, is that a neutron splits and becomes a proton and an electron. So a proton is 1, 1, because its charge is 1, then its mass is 1. An electron is -1, 0. Now, if you add those together, oh, I'm sorry, a neutron is 1, 1, or is 0, 1. 0, 1. So if you add all that together, it works. 1 plus -1 is 0. 1 plus 0 is 1. And that kind of explains what's going on. So the neutron splits and becomes a proton and an electron. The proton stays in the nucleus and increases the atomic number by 1. And then the electron gets emitted, and that's the beta particle. Now, you don't have to remember all that, but if it seems weird that the atomic number would actually increase, even though we're losing something, that's why. Because we're losing the electron, but we're gaining a proton. Or the neutron is becoming a proton. All right, so let's try one. What do you get via the beta decay of yttrium 90? Yes, that's a Y. There is. 39. Just think I'm up here just like making shit up. Yeah. All right, so what do you get? Zirconium, yeah. So we got our beta particle and then zirconium 90.
So all we're doing is just -1.
Mm-hmm. Yep. So that's beta decay. Beta particles, what do you think about their, so they're high energy electrons. How do you think that compares to what we said about alpha particles? Oh. What did I do? Oh. So you think they're smaller or larger than alpha particles? Smaller, much smaller, right? Because they're just an electron, so much, much smaller. They are still charged. Are they more or less charged than alpha particles? Less. Yeah, an alpha particle is +2. A beta particle is -1. So less of a charge. They're smaller. And so what would you expect about like how far they can travel through air or through stuff? More or less? More, yeah, that's right. So beta particles can penetrate more through stuff than alpha particles could. And so that type of radiation can potentially get more like something you need to shield yourself from if you are exposed to it, rather than just be concerned about getting inside. There's other, and we're going to look at some other ones next, but there's also, we think of all this stuff as like being bad, but there's a lot of good things about radiation too. If you talk about radiation like therapies, but also imaging, that's kind of a neat use of radioactive isotopes. If you can get something like a beta emitter or a gamma emitter that we'll talk about, you take some sort of a pill that has that element in it, the element goes to a specific place in your body, and then it shoots off this radiation that makes its way out of your body. You can detect it as it's coming out, and then you can get really good pictures of these internal structures in your body based on what kind of radiation is coming out and where. So there's some neat examples of that in the book that show that. All right, let's look at another one. What? Charlie decay? No. Good guess though, kind of. We'll get to that one. Positron. This one doesn't get a neat name. This is the emission of what we call a positron, which is not a particle we've ever talked about before. A positron is the, well, it's written like this. It's written the same as an electron, but with a positive charge. So it's sort of, it's kind of like the opposite or the anti-electron. In this case, it's similar to the beta emission, but instead of a neutron decaying, a proton decays. Into a neutron and a positron. So with positron emission, you're doing the same thing, but it's actually a bit more straightforward than the beta particle. Again, we just need to have those particles add up. So we've got 12 and 24, which is magnesium. Let's see if they have a picture here. Here it's on 153. No, we're not going to see it. So down here, there's a brain scan called PET scan, or positron emission tomography. And what is happening here is you put radioactive isotopes in the body, they go up to the brain, and then these particular isotopes emit positrons. Now, positrons are actually extremely short-lived, because as soon as they hit an electron, it's kind of like matter and antimatter. They are destroyed and produce pure energy, also known as gamma rays. But when that happens, those rays exit the body. And so you get these really good images of what's happening in the brain based on where these atoms are going, where these radioactive atoms are going, and releasing their positrons, which then become gamma rays and can get detected by special equipment. So this is a common imaging technique. It looks like this. In this case, they're looking at brain function of a normal brain versus a brain affected by Alzheimer's disease. So you can see the activity levels significantly different in different parts of the brain over on the right. And that's the positron decay. But then the last one that we're going to look at is gamma decay. And this one's a little strange because a gamma ray is not a particle. because it's not a particle, it doesn't have any charge, it doesn't have any mass. It's just high energy light. So you just write the letter gamma with 2 zeros because there's 0 charge, there's 0 mass, just 0, 0. So that's going to make writing our equations a little difficult because if we don't have any numbers, then we can't subtract anything and find out what's left. So what happens in gamma decay or gamma emission is that we're actually not changing mass, we're just changing energy. So a gamma equation always starts with what's called a metastable nucleus. And the mass number is written with a little m for metastable. Meta means like half, partially. So it's partially stable, not quite stable. And that means it's higher energy than it would like to be. So when it decays, it emits that gamma ray and then stabilizes itself like this. So no numbers change, all you lose is the m. And now you have a more stable nucleus. These metastable nuclei are usually products of other processes. So some other decay reaction might cause or result in a metastable nucleus, and then that metastable nucleus has to relax and release that gamma ray. All right, so things about gamma rays. They are pure energy. Which is a form of light. So they don't have any mass. Which means that they are extremely penetrating. They can go through whatever, because they can actually pass in between the nucleus and the electrons of anything. So when we get our lab equipment out, when we look at some of this nuclear stuff, we'll be detecting gamma rays coming from space because there's just gamma rays all over the place all the time. They come from, the sun or wherever else, some other sun in space, and they can go that far without hitting anything. So from a health standpoint, that's good and bad because gamma rays are more likely to pass through you than to hit anything inside of you because they're so penetrating. But if you're exposed to a whole lot of gamma rays, then you're exposed to a very large amount of energy. And once you have a greater probability that something's going to hit something important in there, that's when it can start causing problems. So high energy very penetrating and so if you're exposed to a large amount of gamma rays, there's a better chance that some of them are going to hit your atoms in your body. And when they hit your atoms, they can knock electrons off, which can then cause DNA to fold back on itself and do all kinds of stuff that's not supposed to do. And that's why you get irregular cell growth, things like cancers from radiation, because of that kind of behavior. When you knock those electrons off, you mess with molecules like DNA, then the cells aren't going to do what they're supposed to do. So that's why there's a risk to some of this stuff. It's also why it can be used therapeutically. So you can send radioisotopes or these rays directly to different parts of your body and have them knock out cells that aren't supposed to be there. So things like radiation therapies for cancer use that high energy source to try to destroy cells that aren't supposed to be in your body. Okay, so that's the various types of radioactive decay. So make sure you understand how to write those types of equations, that you can write those equations. like I said, it seems like these are a little easier than what we did before, so it shouldn't be too much of a problem. So the last half of the chapter is on the other side of how do we measure radioactivity, and then how does it change over time. There's a couple important ways that we have to measure radiation. One is we want to know how much radiation is coming off of something. And then the other way is to know how much radiation you are being exposed to. So more like a health thing. Oops, spell it right here. So to measure emission, how much actual radiation is coming off of something, there's a couple different units we use. One is the Curie. Which is the number of nuclear disintegrations, or we'll just say disintegrations, like just particles that are falling apart. In 1 second for 1 gram of radium. So that's kind of what this is based on. You have a gram of radium, and you measure how many alpha particles are coming off of that gram of radium in 1 second, and that's a Curie of radiation. Now that's very specific to this type of element, so then of course you can have like millicuries, megacuries, whatever, depending on how much you have. Another radiation activity one is called the becquerel, or BQ. Which is just disintegrations per second. You don't have to know all these definitions and things. I'll show you what we're going to do to use these measurements, use these units. All right, so those are the 2 units we're going to use to measure radiation coming off of something. The other side of that then is absorption. There's a few different units here. We're going to focus on 2 of them. The rad, or radiation absorbed dose. That's just the radiation absorbed by 1 gram of something. So that something could be like body tissue, it could be a detector, a rock, or whatever. So how usually we care about our body, so it's how much is absorbed by a gram per gram. So that's the rad, the radiation absorbed dose. But this is actually not the most commonly used measurement because, as we talked about before, different kinds of radiation have different effects on people. So if we really want to know, like, how much radiation are you exposed to, how much are you at risk, we need a measurement that actually corrects for that. And so the other one that we use is called the REM. And this is the more common one, which is the radiation equivalent in humans. And we'll just say that's corrected for the different types of radiation. So for instance, alpha particles do more damage than some of the other ones, than beta particles. So a rad of alpha particles is worse for you than a rad of beta particles. So the REM attempts to correct that by having some factors that you multiply things by. We're not going to get into all the calculations there. You can look it up in the book if you're interested. But if you look at like how much radiation you're exposed to, or charts about safety with radiation, that's always going to be measured in REM. So here's a sense of how much a REM is. There's a nice thing from this, a nice chart from this, it's actually a comic on the internet called XKCD. And I'll zoom way out here. The idea of this chart, if you can kind of see it, is you take things that are really, really small amounts, and then all of that fits in this. Things bigger amounts, all of that fits in here, then all of that fits in here. And so these are like the really big ones, right? So you see how that kind of flows before I zoom in? So here's the small ones, the bigger ones, the bigger ones, the bigger ones, right? So let's start on the big side. If you were 10 minutes next to the Chernobyl reactor core after explosion and meltdown, that's how much radiation you would have been exposed to. So that's like catastrophic, ridiculous, biggest disaster in history, amounts of radiation when you're right there. They're actually using a different measurement called the sievert, which is the SI unit, but it's similar to the REM. It's actually 100 REM is a sievert. All right. So if we just take a small portion of that, we get here where each little block is, each little orange block here is 10 millisieverts, which would be about a REM. So I don't know if you can read this, but here is the fatal dose of radiation. If you get 8 sieverts of radiation, which is 800 REMs, that's it. Not much you can do. If you get half of that, you could maybe survive it. All the way down to, if you get just 50 millisieverts, that is the 1-year dose limit for a radiation worker. So if you if you're working close to radiation, that's the most you can get in a year and be all right. The lowest dose that's actually linked to increased risk for cancer is about 100 millisieverts, so double that. So half of the lowest known dose is what you could do if you were working with that stuff, if that's what you chose to be your job. All right, so now if we take that even smaller and we take just a tiny fraction of those things, there's that 50 millisieverts again, that dose, but now in green squares. So green square is much smaller. All right. So we go down from here. This is how much you would get if you got a CT scan in your chest. So not a huge amount, but that is one of the things that can be limited over time. So if you've gotten chest CT scans, they will log that for the rest of your life, and there is a limit to how many you can get before you start to have an increased risk of cancer from that radiation. And that's X-ray radiation, that's not nuclear radiation. Here is our normal yearly background dose. So I don't know if you know this, but we're all getting irradiated by radiation all the time. It comes from radioactive elements in the ground, building materials. Buildings are made from bricks, right? Bricks have rocks and stuff in them. Some of those are radioactive, so we're getting some radiation from that. We're getting radiation from space, from cosmic rays, X-rays, gamma rays coming in from space, all that stuff. About 85% from natural sources, and about 15% is an average of like X-rays and stuff that you get for your year. So that's your just normal baseline dose that all people are getting with radiation. So you see some different ones. Even stuff like natural potassium in the body, right? That's giving you some radiation just because there's some radioactive potassium in your body. All the way down to a single chest X-ray. All right, so then if we get to the really tiny doses, you're actually getting radiation by sleeping next to somebody because there's radioactive stuff in there, right? But then the interesting stuff about this is like some of the stuff that people are most worried about is actually the smallest doses, like living by a nuclear power plant for a year. You're actually getting like almost nothing. You get more from your banana, from eating a banana, than a year living by a nuclear power plant, right? Things like using a monitor, you know, I don't know if anybody remembers, there used to be, computer monitors used to not be flat, and they'd be like really big and long, and like, so that was cathode rays. If you go up high in the mountains, you get exposed to more radiation because it's coming from space and there's less atmosphere for it to absorb it. And then just things like dental x-rays, that's about a day of normal radiation. You take a flight, you get exposed to a bunch more radiation because you're way up high, you're getting more radiation from space, less atmosphere blocking you. So I like this chart because it shows like definitely radiation is a dangerous thing that can hurt us, but it depends on the dose. It's not like every bit of radiation is bad for you. It's once you exceed a certain amount, you could be increasing your risk. And that's true for so many things in life, especially with health. It's not about excluding any trace of something. It's about thinking about what kind of a dose is safe and what kind of a dose is not. All right. So the last thing we're going to do is look at this idea of half-lives. Oh, I should also note, gamma rays don't turn you into a superhero, as far as we know. If you have any evidence to the contrary that isn't movies, let me know. But what? The thing is, like, a lot of people have tried, like, inadvertently by, like, you know, being hurt by radiation, and they didn't become superheroes. So I'm not sure that's a great argument. All right. Radioisotopes are often described by something called a half-life, rather than some other way of doing it. And the reason is that individual particles can either decay or not decay. So if you look at a single atom, it either does the reaction or it doesn't. It doesn't like partially do the reaction and then partially do it later and partially do it later. So at any instant, any particular atom, radioactive atom, is either decaying or it's not. So this binary idea of either it is or it isn't means that over time, what's really happening is this thing is decaying by getting cut in half. Right? So think about it this way. We could do this as a demo, but maybe we'll do it when we do the lab. You could take a bunch of coins, take like 10 coins, right? You throw them in the air and they all land. And the odds are about 5 are going to be heads and 5 are going to be tails. So let's say heads means it decays, tails means it doesn't decay. So then you take those 5 that didn't decay and you throw them again, and about half of those decay. You take those that didn't decay, throw them again, about half of those decay. So that's what happens with atoms as well. At any given time, about half of them can be decaying. So the half-life is the amount of time it takes for half of a sample of whatever to decay. All right, so let's look at this beta decay reaction for an example. Iodine 131 undergoes beta decay. To become xenon. So at the very beginning of this process, you got your sample of iodine 131. Let's say you have 20 milligrams of iodine 131. So we're going to start with 20 milligrams of iodine. So that means how much xenon 131 do you start with? Look at the reaction. If you start with 20 milligrams of iodine 131, how much xenon is there at the beginning of the reaction? There's 0, right? Because that's a product and none has formed yet. So at the very beginning of the reaction, you start with 20 milligrams of reactant and 0 milligrams of product. All right, so then this stuff starts decaying. After 1 half-life, we have half of the iodine that we started with. That's where that term half-life comes from. And so that means that we have the other half has become xenon, but hasn't disappeared. It's just decayed into something else. After 2 half-lives, we split it in half again and say 5 milligrams. And that means the other additional amount is xenon. Another half-life, we split it in half again. And so on. So with successive half-lives, you're splitting the amount that you have in half each time. And then we can put a time on that. So for this particular isotope, iodine 131, the half-life is 8 days. So if you had, yeah.
Why is it going from 10 to 15? Why is it increasing?
Because that's the product. So the iodine is decaying and becoming xenon, which means more and more xenon is being made. Just like any other chemical reaction. If you're losing reactant, it's becoming product. So you're losing this is decaying, and it's forming this.
Wouldn't it be 20? Since 10 before? 10 and half that would be.
Well, you always have to have the same number of mass total. So if you start with 20 milligrams of this, half of it becomes xenon, you still need 20 milligrams total. So the two of them together have to add up to 20. See, 10 plus 10 is 20, 5 plus 15 is 20. So then down here you'd have 17.5 milligrams of xenon. So as that iodine decays, it becomes xenon. Yeah. So the half-life of iodine 131 is 8 days. So when we say 1 half-life, 2 half-lives, we can also count that in time measurement like days. So we can say 1 half-life is 8 days. 2 half-lives is 16 days. 3 half-lives is 24 days. So we're running out of time a little bit here. But let's take a look at an example. On page 149. So phosphorus 82, a radioisotope used in the treatment of leukemia, has a half-life of 14.3 days. If you have 8 milligrams of phosphorus 32, how many milligrams of phosphorus 32 remain after 42.9 days? So to figure this out, we have to figure out how many half-lives is that 42.9 days, and then cut it in half that many times. All right, so first, how many half-lives is 42.9 days? How do we figure that out? Yeah, each half-life is 14.3 days. So if we take 42.9 and divide it by 14.3, I believe we get 3 half-lives. So the total time divided by each half-life time tells you that there's 3 half-lives in those 14.3 days. So then to solve this, we're going to cut that initial amount in half 3 times to figure out how much is going to be left. So you would start with your 8 milligrams. After 1 half-life, you've got 4. After 2 half-lives, you've got 2. So then after the 3rd half-life, you've got 1. So that means you'd have 1 milligram left after 42.9 days. The trickiest part of this is remembering that it's different, that it's about cutting things in half successively rather than just dividing by something. So when I ask these questions on quizzes and exams, a lot of times people say we'll take things like, okay, 8 milligrams divided by 42.9 days is whatever. Or they'll figure out the half-life part and say, okay, it's 3 half-lives. So then 8 divided by 3 is the answer. But it's not. It means it's cut in half 3 times. So you can't set this up like a regular conversion problem. You have to cut it in half over and over again, however many times is necessary. All right, let's do one more, and then we'll practice this more on Wednesday because we're just running out of time. But the other way that you can do this is using radioactivity. So I'm looking for an example. Where's the one that we... Yeah, okay, 5.68. So this is 162. But we can also track half-lives in radioactivity. Rather than saying something, a certain amount of something is decaying to less of it, we can say a certain amount of radioactivity is going down. In this case, we've got oxygen 15, half-life is 124 seconds. If we start with an activity of 4,000 becquerels, how many minutes until we've got 500? So it's not it's not the amount that we're interested in. It's not like grams, milligrams. It's the radioactivity, the becquerels. So to do a problem like this, you've got to figure out how many times do I need to cut this thing in half. That's my number of half-lives. And then multiply that by however long one half-life is. So 4,000 becquerels. If we keep cutting it in half, and we just sort of like count how many times we cut it in half, so we've cut it in half, we get 2,000. We cut it in half again, we get 1,000. Cut it in half again, you get 500. Not 5,000, 500. All right, so we got from 4,000 to 500 in 3 times cutting it in half. So that means 3 half-lives. So that's 3 times 124 seconds, which would be 372, right? 372 seconds, I think. And then we convert that to minutes by dividing by 60. Do I still not have a calculator? I do know. Nope, it's on the calculator. All right, so 372 seconds, do whatever, we can convert that to minutes. So the point of showing this example is when we look at half-lives, we can either look at it with regard to the mass or with regard to the amount of radioactivity, but the process is the same. You cut it in half a certain number of times. Each time you cut it in half, one half-life has elapsed. There are equations for like figuring out what happens, how much is left in the middle of a half-life, but we're not going to focus on that in this class. We're not going to worry about that. So in this class, it's going to be even half-lives. If you cut it in half a certain number of times, what do you have left and how long does that take? All right, sound good? So start working on this. We've got acid-base lab on Wednesday, but then we're also going to finish up this chapter because we'll do a quiz on this on Monday, on the nuclear stuff on Monday. So start working on that. The only thing we still have to do is talk about fission and fusion, which is the last bit of that chapter, so we'll catch that up on Wednesday.